Hello everyone, welcome to this video entitled Autopsy of an LED bulb. This is the outline of this presentation. First, we will start with an introduction. We will show the measurements of the different components of the LED lamp. We will show the characterization of the LED array that is used in this lamp. We will talk about the analysis of the converter employed in this LED bulb. And finally, we will show several LTspice simulations that will help us in finding the cause of the death of this LED bulb. This is a relevant video related with this presentation today, LTspice number 30, how to create a hysteresis controller for LTspice, and this is the controller that is used in this LED bulb. So here we can see the different elements of this bulb. This is a lamp that was operating in my house for several years. Here we can see the cap, this is the diffuser, this part here of the bulb. Inside we have the LED array, we can see the different LEDs of the lamp. This is the driver, the electronic driver, seen from the top, and this is the electronic driver, seen from the bottom. So we can see different elements. Here we can see the inductor. We have two capacitors, one is 2.2 microfarads, the other one is 4.7 microfarads. We can also see here the controller, the integrated circuit used in this converter. This is the rectifier and other minor elements forming part of this LED lamp. This is the fuse that was in series here with this cable and connected inside the cap to one of the terminals of the lamp. So usually we say that the most weak element in an LED lamp is the electrolytic capacitor. So we have here two electrolytic capacitors and that the values on them were 2.2 microfarads and 4.7 microfarads. So it is said that when time passes, the electrolytic capacitors are decreasing their capacitance due to the evaporation of the electrolyte, and this is the main cause of the failure of LED lamp and in general of a converter, of a power converter. So what we are going to do in this video is to investigate this a little bit further, try to understand how this lamp operates and try to find out the cause of the failure of this LED bulb. By searching for information about the integrated circuit that is used in this lamp, we can find that it is a non-isolated offline buck LED driver. So this circuit, this converter, employs a buck converter that is going to operate in critical conduction mode. So this means that the current through the inductor is going to be on the boundary, is going to increase from 0 to a maximum value and then go to 0 again and so on. So we will see this later. Also, this integrated circuit has an internal power MOSFET, so we don't need to use an external device for this, and also the circuit incorporates several protections like open circuit, short circuit, under voltage, thermal protections, and so on. So this is the schematic that we have for this integrated circuit. So this is the line, we have a fuse, we have a rectifier, we have here a capacitor, a filtering capacitor, which is of a high value. So this is going to be a DC level with some ripple, but mainly a DC level. Then we use a resistance here, a high resistance, and another capacitor to supply the integrated circuit. The power switch is inside the circuit, as we have seen, and then we have the structure corresponding to the buck converter. We have the inductor, we have the load, the output capacitor is the other big capacitor that we have in the lamp, and then we have the freewheeling diode corresponding to the buck converter. And also there is here a sense resistor to measure the current through the switch and do the control of the converter. And we have another additional resistance here to do the protection, the overvoltage protection. But we are going to focus mainly on the power converter operation. So here we can see the basic operation. When we close the switch, we have an inductor current that is going in this direction through the load and through the output capacitor, and the voltage that is applied to the inductor, as in any buck converter, is the difference between the input voltage and the output voltage, the voltage across the lamp. Then during the off interval, the switch is open, so the current through the inductor goes through the freewheeling diode into the output, and the voltage that is applied to the inductor is minus the output voltage. So the current waveform is going to be like this. It's going to increase from 0 up to a maximum value, which is IP, with this slope here, which is the input voltage minus the output voltage divided by the inductance. And then when the current through the inductor reaches this value, the switch is turned off. So the current is decreasing until reaching 0. And then when the current reaches 0, the switch is turned on again, and this continues with the operation of the converter. So it's very simple, and it operates in the critical conduction mode. The first thing that we have done to analyze the state of the LED bulb was to measure the value of the capacitors. So here we have the input capacitor. It has in principle a value of 4.7 microfarads. We took this capacitor and connected to the impedance analyzer, and we measure a value of the capacitance of 2.25 microfarads. So we can see that it is true that the value of the capacitor was going to decrease due to the aging of the capacitor. We get a reduction of the capacitance of 52%. And in the case of the output capacitor, the situation is even worse. Originally, this capacitor has a capacitance of 2.2 microfarads, and when measured, the value is only 1.35 nanofarads. So this means that the reduction of the capacitance is almost 100% in the case of this capacitor. Also, when handling the capacitors, we have seen that the plastic envelopes have crystallized. They were very fragile and they were broken in pieces. So this is a sign of the high operating temperature for a long period of time inside the LED lamp, which at the end causes the decreasing of the capacitance due to the evaporation of the electrolyte inside the capacitors. Regarding the inductor, which is shown here, we measured also the value of the inductance, and we obtained this value, 4.8 millihenries, with this series resistance. So in principle, in an inductor, we do not expect any big change in the value of the inductance due to the aging and due to the effect of the temperature. So we can assume that this value of the inductance is the original value that was designed for this LED driver. The next thing that we did was to test the LED array of the lamp. For this we have used a voltage source here and a series resistor to supply the current to the LED array. And then we can see that when we increase the voltage, Here, when we get something like 150 volts, the LED array starts operating. So this proves that the problem of the LED bulb was not on the LED array itself, but on the electronics of the LED bulb. Following this process, we measured several operating points of the LED array. Here we have different points corresponding to the voltage across the lamp, and this is the current through the lamp, and this is the power in the lamp. So using this WinPython script, we have represented the lamp current and power versus the lamp voltage. So in blue we can see the current through the lamp, and in red the power through the lamp. The nominal operating point was for 13 watts in the lamp, so the operating voltage is 161 volts and the current is 80 milliamperes. And also from this characteristic, by taking 2 points from this characteristic, we have taken 163 volts and 99 milliamperes and 157.7 volts and 53 milliamperes. These are 2 points from these measurements. Then we can get the series resistance of the lamp, of the LED array, and the threshold voltage of the LED array. So we can obtain the parameters of the model for this LED array. Also, by inspection of the lamp, we found that the input fuse was blown out, so this has failed. But the rectifier and diodes were not damaged, so they are okay. And also the output diode is operating, so it's not damaged either. And also the internal MOSFET of the integrated circuit was also in good standing. Other important values that we have measured were the series resistance used for the power supply of the integrated circuit, here 250 kilo ohms, and the capacitor in parallel with the power supply of the integrated circuit is 1 microfarad. And finally, the series resistance used to measure the current through the switch, which is the same as the current through the inductor when the switch is on, is 2.4 ohms. So now let's study a little bit the operation of the original circuit when it is brand new. Then we should have here a capacitor of 4.7 microfarads and at the output 2.2 microfarads. This is the value of the inductance, 4.8 millihenries, and this is the series resistance to measure the current through the inductor. And internally here the integrated circuit has a voltage of 0.4 as a reference to detect the peak value of the current in such a way that the switch is going to be on until this value IP, and this value is given by 0.4, the input voltage, the reference, the internal reference, divided by the value of Rs, and the value of Rs now is 2.4 ohms, so this means that the peak value of the current is 166 milliamperes. And then because we are operating in the critical conduction mode, the average current that is going to circulate through the LED array is 1/2 times the peak value IP. So this means that we will get an average current through the LED array, which is 83.3 milliamperes. And it matches the expected value that we have seen before from the characteristic of the LED array and the power of the lamp, which is around 13 watts. It's also interesting to calculate the voltage that we are going to have here, the DC voltage that we are applying to the buck converter. So we can assume that due to the filtering of this capacitor, we are going to have approximately a sawtooth waveform at this point, VG, with an average value, which is this value, uppercase VG. So this is the typical approximation for a capacitor-based filter in which we are assuming that the current is circulating from the capacitor during the whole semi-period. So the peak-to-peak voltage report that we are going to have can be obtained very easily from this expression, and also the average value is given by the peak value, which is 325 volts minus half of the voltage ripple. So from these two expressions here, and knowing the different values, then we obtain the average voltage that we are going to have at this point here is approximately 275 volts, and the peak-to-peak voltage ripple is 100 volt. And finally, from the evolution of the current, we can obtain also the T-ohm time using this expression. So, for example, if we use the average value, 275 volts, we will get an on time of approximately 7 microseconds. The off time, this time here from T-on until T, it can be also easily calculated because it's going to be IP divided by the slope during the off time. So we get this value is 4.95 microseconds. So finally, the switching frequency at the average voltage is 84 kHz. Of course, the switching frequency is going to change because we have a ripple superposed here to VG. So when the voltage VG is greater, then the on time is smaller. So the switching frequency is going to be higher. And when VG is lower, the on time is larger because we need more time to reach IP, and therefore the switching frequency is going to be smaller. Note that the T off time is constant because the peak current IP is a fixed value, and also the output voltage is the lamp voltage, so it's also fixed. So now let's do a simulation to better understand the behavior of this converter. Here we have the basic converter. This is the input voltage, the line voltage. We have the rectifier here, the filter capacitor, and then here we have the buck converter. And we are using to do the control of the switch this circuit that we developed in a previous video. Is my hysteretic controller, and you can get information about this component in this video, LTspice number 30, how to create a hysteresis controller for LTspice. So what we are doing here is to measure the current through the inductor using this sensor here and sending this information into the controller, and we have the value for the peak value of the current. So we have selected the value that we have seen before, 166 milliamperes, and for the valley value we have selected a very small value, so we are going to operate in critical conduction mode in the boundary between continuous conduction mode and discontinuous conduction mode. So we have selected here 0.1 milliamperes. Then at the output we have the signal for the switch, and then we have the gate driver, and then finally the MOSFET here. We are going to do a simulation up to 60 milliseconds, and we are saving information for the last 40 milliseconds. So now we can run the simulation and see the operation of the converter. Here we are representing the voltage at this point, so it's equivalent to what we have called before VG, and then maybe we can add another pane to see other signals. For example, the current through the inductor here at the output of the sensor. So we can see that the current through the inductor, the peak value of this current is almost constant. We can take a look at a small interval. So we can see that this value here is almost 0, and this value here is similar to the value that we have chosen. In fact, it's a little bit higher due to the delay in the operation of this switch, but we are not going into this in detail right now. So we can see maybe other waveforms. This is the voltage here, as we have said before, and maybe we can add another pane and see the output voltage, the voltage across the lamp. So it will be between this point and this other point. So here we can see the voltage across the lamp. The average value is 162 volts, very similar to the value that we have calculated. The average value for VG is again something similar, 285. Remember that we have neglected this interval, the charging of the capacitor. We have assumed that the charging was very quick, so we have some difference, but we are not interested in entering in this detail either. But in general, we can see that the converter is operating as expected. So now we are going to do a simulation with the values of the capacitances that we have after many hours of operation when the lamp failed. So now let's do a simulation with the circuit after the failure. So after many hours, we have a capacitance here of 2.25 microfarads, only 50% of reduction. And here at the output, we have a capacitance of 1.35 nanofarads, very, very small, almost 100% of decrease in the output capacitance. The rest of the circuit is exactly the same, so we can now run the simulation and see the results. We can, as in the previous case, take a look at the voltage here, which is VG. So we can see that now the ripple has increased, obviously because we have here a lower capacitance. And also the average value is smaller, 252 volts. We can maybe add another pane and take a look at the current through the inductor. We can see that the peak value is also controlled because we have our hysteretic controller here. We have some intervals in which we have no conduction because this low value here of the voltage at this point, the VG, is close to the threshold voltage of the lamp, but otherwise in this interval we have the same current as we have seen before. It's very, very similar and is operating in critical conduction mode. In fact, this controller is limiting this peak value, so the current is always under control. We can maybe take a look at the voltage across the lamp. So this should be between this point and this point. So this is the voltage now. Because we have no filtering here due to this capacitor, the voltage is also high frequency. Maybe even we can add another pane and take a look at the current through the lamp. So we can see that all the waveforms are very similar and they are high frequency because we don't have filtering due to the very, very small value of this capacitor here. But in principle, there is no any problem in operating in this way. There is no reason for failure because of this, because we have current well controlled through the inductor. So I think that the failure must be in other part of the circuit. So my guess is that the failure of the lamp was due to the power supply here of the integrated circuit. They use a series resistance and this capacitor to do the filtering and do the supply of the integrated circuit. But this integrated circuit has two thresholds for the operation of the integrated circuit. One is the turn on threshold, which is 13.8 volts. So when the voltage here is increasing, the operation of the integrated circuit is going to start when the voltage reaches this value here. And then when it is operating, if the voltage, the supply voltage here decreases for any reason and goes below this value, the turn off threshold, which is 9 volts, then the integrated circuit is going to stop the operation, the switching of the switch. So when this capacitor here decreases the value of the capacitance, then the average value, as we have seen, also decreases, the ripple increases, and this can distort the voltage at this point. So maybe the circuit even can start oscillating, because depending on the consumption of the current by the integrated circuit, then this voltage can be higher or lower, and then we can go below the threshold voltage, then turn off the switch, then the consumption is going to decrease, so this voltage is going to increase again, going above this value of 13.8 volts, and we can see even oscillations in the output of the lamp, in the light of the lamp. So we can see even flickering in the LED lamp, and eventually, due to this turn on and turn off of the converter, the fuse is going to blow up. To check this idea, let's do a simulation including the power supply of the integrated circuit, which we are showing here. So we have the series resistance, the filter capacitor. This is a zener, which is a zener internal in the integrated circuit, which is 17 volts. And this is to emulate the load corresponding to the integrated circuit. So we are consuming 1 milliampere with this current source. And we can do a simulation with the original capacitances, 4.7 and 2.2 microfarads. And then I have done already the simulation, so we can do tile. So here in this part we have the circuit with the original capacitors, and these are the waveforms. This is the voltage VG at this point, and below in blue is the voltage at this point here. So we can see that it reaches the value of 17 volts and is operating well. But in this case, when we use a capacitor of only 2.25 microfarads here and 1.35 nanofarads here, which are the old capacitors, then also we can measure here the voltage VG at this point and the voltage here at the input of the power supply of the integrated circuit, and we can see how now we cannot reach the minimum value corresponding to the operation of the integrated circuit. So finally, we can conclude that mainly the effect of this capacitor here, the low value of this capacitor, is affecting the power supply voltage of the integrated circuit, and this is the main cause of the death of our LED bulb. Well, this concludes this presentation today. I hope that you find this video useful. Please let me know if you have any comment or question, and I hope to see you in the next video. Goodbye now.